Now let's talk about insert function. And as I said, in the data structures, we have two main functions. First one is insert, and second one is delete. Right? So these functions are kind of fundamental functions. Basically, we need to add new data, and then sometimes we need to delete some data, right? And then we have some other functions like a search and the sort or something. Okay, so let's talk about the insertion functions with the binary search tree. Okay, so basic idea is quite simple. First, try to search the key. Okay, so we talked about the search functions. So when we insert one new data, then let's say this data has a key too. So we have a key and data, right? So we have one node, okay? And then we want to insert this node in the middle of a tree, BST. And we have to find the perfect location for this new node. So this basic idea explains how to find their locations. First, try to search the key. Okay, if the key is found, then it already exists in BST. And do you remember that one of the constraints of BST says that the key is unique. So we cannot have the same key again and again. So if the key is found, then we cannot add that node. Okay, we have to quit. Good. Otherwise means there is no such key in the BST. Okay, then when we follow these search functions, then basically if we don't have that key in the tree, then basically we will meet a null pointer. Okay, so then insert the key there, insert the node there. Okay, so let's try to understand what I'm saying here with this example. So given this BST, okay, 30 and 5, 40 and 2, okay, it's given. And then now we want to insert 80, okay. Then first we want to search 80 first. So we check the root node 30, and 30 is smaller than 80, so we go to the right child, and 40. Now we are facing 40, and we compare 40 to 80, and 40 is smaller than 80, and then we go to the right child. Okay, right child of 40, and it is null. So we can be sure that we don't have 80 in the BST. Okay, then we put 80 there. Perfect. What if we insert 40 here? Then we first check 30, and 30 is smaller than 40, and then next we move to the 40, and then when we compare these two keys, then 40 is the same as 40, then we know the key is already there, then we cannot add that key anymore. Okay, so let's try to insert 35 from the second tree. Okay, so first we have to compare the root node. Okay, then the 30 is smaller than 35, and we move to the right child. So we compare 35 to 40, and then 40 is larger than 35, and then we go to the left child, and left child is empty. It is a null pointer. That's the perfect position for a 35. So we insert the 35 there. Okay, let's try one more thing. So what if we want to insert 37? Okay, then we compare 37 to 30. Okay, then we go to the right child, and 40 is larger than 37. So we go to the left child, and 35 is smaller than 37, and we go to the right child, and which is null. So 37 will be the right child of 35. So you know what to do, right? In the previous slide, I described the algorithm of insertions. Okay. Then basically, if we don't have the same key in the BST, then we find the right place for a new key. Okay, and then the right place is actually the null pointer of one node. Okay, for example, in this tree, in this slide, we have a small tree, BST tree, and if we want to add a new node with the key 45, then the right place is null pointer in the blue color. Okay, So we just find the pointer for the place. Okay. Then if we go there, it means if the tree is pointing that null pointer, then basically, we lose the information about the positions. Null pointer is null pointer, it is not pointing anything. So basically, if you want to add something at the blue null pointer, then we have to have some pointer pointing at 50. Okay, then we can arrange. We can manage the 50's left child pointer. Okay, so after allocating memory space for the new node, and assign the data into the node, and then the 50's left child pointer will point that node. Okay, that's how we add that. So do you see that? Instead of just searching the place, we need the parent's pointer. Okay, so if you want to add something at the blue null pointer's place, then we need the pointer pointing at the 50. Okay, if you want to add something at the null pointer in the red color, then we need a pointer pointing 60. Okay, so we have to modify the search function slightly. So instead of just going there, instead of going to the null pointer, actually we have to stop at the parent pointer. Okay, at the parent node. That's the main kind of modification of this modified search. So let's follow this implementation. So first, we start from the root node, and basically this modified search is kind of modification of the search function in the iterative solution. Okay, so this is not the recursive solution, by the way. Okay, so we have a while loop, and in this while loop, we check the root node. So we check the root node's key. If that's the key, if that's the target key, then we return null. It means the key is already in there, so we cannot add a new key there. Okay, else means, okay, we don't have the root node is different from our target node. And then we check if the target key is smaller than the tree key, then we should go to the left child, right? So instead of going there directly, then we check one more thing. So we check if the tree's left child is null. If that's the case, then instead of going there, we just return tree. So if you look at this figure, okay, then this case corresponds to the null pointer in blue. Okay. So tree is a pointer here, and tree is pointing the node 50. Okay, and then the key is, let's say, 45. Okay, then and 45 is smaller than 50, so we actually go to, following the previous search function, then we go to the left child. So we will go to the blue null pointer, but instead, we check this one. So tree left child is null. Okay, 50, so left child pointer is null, so we return pointer tree. Okay, then we can add a new node at the place of blue null pointer. Okay, and then 50's left child will point that. Okay, good. Otherwise means the 50's left child has something. It's not null. Then we actually move to that child node. Okay, and likewise, in the next else statement, likewise, if we check if the right child is null pointer. So if the right child is null, then we return a tree pointer. Otherwise, we go to the right child. So the null pointer in red color corresponds to that case. Okay. So let's say we are adding a new key, say 70. Okay. Then so tree is actually pointing 60. Okay. So currently tree is pointing 60. And 70 is larger than 60, but then we can check the right child. And in this case, right child is null, then we return a pointer pointing at the node 60. Okay, so basically, instead of going to the right place, once we find the right place, then we return the parent node, okay, instead of the current node. So basically, the target place is all the time, the target place is null pointer. So instead of returning the null pointer, then we return the parent's pointer. Okay, so basically, if you remember the linked list, when we delete one node from the linked list, then actually we had one pointer following this linked list, and at the same time we had another pointer following the current pointer. Okay, so it was like a tail pointer, and tail pointer is pointing kind of the parent node. Okay, the tree is kind of extension of the linked list. So in the linked list we have only one child, but in the BST we have two children. Okay, so when we manipulate something on the node, then we need a parent's pointer. We have to manipulate the parent's node's pointer. Okay, so likewise, when we insert new node, then we need the parent's node's pointer. Okay. Now let's talk about insert function. Okay. So from the previous slide, we have a modified search, which returns the parent pointer of the target place. So for example, in this figure, if we want to insert 45, then the target place is the null pointer in blue color. Okay, then the modified search will return a pointer pointing at node 50. Okay, or if we want to insert something like 70, then the modified search function will return a pointer pointing at node 60. Okay, so we get the parent node. Okay, good. And then now we check if the parent is null or if the tree is empty. So if parent is not null, it means we have the right place to put the new node. Okay, or even when the parent is null. Okay, if the parent is null, usually when we add something like 50 in this example, when we add a new node with the key 50, then the modified search will return the null pointer. Okay, so if we want to insert key 60, then it will return null pointer. Or if the BST is empty, completely empty, there's nothing there, then there is no such a thing like a parent node. In that case, parent will be null pointer too. Okay, and even when the parent is null pointer, but still, if the tree is empty, then we should be able to add something, right? So when we add something for the first time, then the parent is null. So we have to check if it is empty too. So if it is empty, then we can add something. So first, we need to allocate memory space for a new node. Okay, so PTR is pointing that. Good. And then we assign the key. Num is the key. Okay, so the PTR key will get the num, and the PTR left child and right child, they are all initialized as a null pointer. And in this implementation, we forgot to add the data field. Okay, so basically we have to assign the data to PTR data or something. Okay, but in this slide we don't care the data part that much because we are interested in how it works. Okay, so let's assume that the data field is already set. Okay, now let's check if it is empty. If it is empty, that means root is null pointer. Okay, root is a private member of this class, BSD class. Okay, now root will be the PTR. So root is pointing the new node. Okay, good. That's it. Else means the tree is not empty, but parent is pointing something. So parent knows which actually parent means the right place is parent. Okay. So in the modified search function, actually we know which child is the right place. Is it the left child position or right child position? We know that, but instead of returning those kind of information, we just return the parent node. parent pointer. So in these functions, with this parent node, then now we have to figure out which child position is the right place one more time, okay? Because we lost that information in this function. So first, we check if the num is less than parent key, which means, oh, now we know the new node should be the left child of this parent. So parent left child should be the PTR. Else, otherwise, parent right child should be PTR. Okay. In this case, we don't have to care about the case where a num is the same as parent key, because in that case, parent is null pointer. Okay. So this is an insertion function. Okay, good. Now let's talk about another kind of core function of BST, which is deletion. Okay, and the deletion is a little bit more complicated than insertion. Okay, so we have to break this function into a couple of different cases. Okay, first, deletion of a leaf node is easy. So in this slide, we have example from the left figure, from left BST. When we delete 80, okay, then it's simple, just delete it. Okay, then and 40's right child should be the null pointer. Okay, that's simple. And second, deletion of non-leaf node, but with a single child is also easy. Okay, so we are not talking about non-leaf node with the 2 children. Okay, so we are talking about non-leaf node with a single child, like node 5 in this figure. Okay, so in that case, delete that node, okay, and then attach its single child to its parent. So in this example, we want to delete 5. So we will free a node 5, okay, and then at the same time, node 2 should be the left child of 30. Okay, because think about this one, the constraint of BST, okay, the one constraint of BST, the nodes of the left subtree should be smaller than the parent node. Okay, the keys of the left subtree should be smaller than the parent key. Okay, so all the nodes on the left side are smaller than the root key. So 2 can be the left child of 30. What if we have a 7 instead of 2? Okay, instead of 2, what if we have a 7 as a right child of 5? Okay, in that case 2, okay, is simple. So we delete 5 and 7 will be the left child of 30. Okay, so either way will be either case will be the same. So if we have just one left child, or if we have just one right child, okay, that's the same case. So delete 5 and 2, node 2 will be the left child of 30, or delete 5, node 7 will be the left child of 30. Okay, don't get confused. I'm talking about the case where we have we delete one non-leaf node with a single child. Okay. And there is the third case, which is not that easy. Okay, so we want to delete one non-leaf node with 2 children. Okay, so for example, in this figure, on the right side of this slide, we have a little BST. So we want to delete 30, or we want to delete 40. Okay, so when we delete one non-leaf node with 2 children, that's not easy. Okay, so let's start. So basically, we will replace the root with largest element in its left subtree, or smallest element in its right subtree. Okay, that's the key. So I mean, when we delete a 30 in this figure, then the largest element in its left subtree, which is 5, okay, so 5 will go into a 30, okay, or the smallest element in the right subtree, which is 35. 35 will go to the root node. Okay, so that's the basic algorithm. Okay, so there is a note here. The largest node in its left subtree is a leaf or a node with a single child. I mean, the largest node in its left subtree is 5. Okay, and the 5 doesn't have 2 children. It has only 1 child. Okay, let's look at the right subtree. So in the right subtree, the smallest node is 35. Okay, 35 has no children. Okay, so all the times, the largest node in its left subtree is a leaf or a node with a single child. It cannot have 2 children. If it has 2 children, then that's not the largest node because the right child is larger than itself. And likewise, in the right subtree, the smallest node in its right subtree is a leaf or a node with a single child. Okay, so if it has 2 children, then that's not the smallest node because the left child is smaller than that. Okay, so all the time, largest one. Okay, so let's focus on the left subtree. Okay, the largest node is a leaf or a node with a single child. Okay, so in the previous slide, we talked about this case. So basically, the algorithm is like this. If we move 5 in this figure on the right side, if we move this 5 after deleting 30, then the largest node in its left subtree is 5, and we move 5 to the root node. Then the original place for node 5 is empty. So we just change the problem into another problem. Okay, so in the another problem, it says, oh, we want to delete 5. Okay, because we just moved the 5 into its parent. So if we delete the 5, that's a simple case because in the previous slide we did that. Or if we move the smallest node in the right subtree, then after deleting 30, then 35 will go to the root node. Okay, then we just change the problem into another problem saying, oh, now we want to delete the 35. Because we just moved the 35 to the root node, then we have to handle this empty node. We just deleted the 35. You know what I'm saying? So basically we want to delete 30, okay? The node 30, but if we move the largest node in its left subtree, then the 5 will move to the root node. So in the place of 30, the 5 will go there. And then 5 is empty, so we are deleting 5. Okay, or I think I'm repeating the same thing again and again, but let me repeat one more time. So if we choose the smallest node in the right subtree, which is 35, okay, then it means, okay, so we want to delete 30, but so now 30 is gone, and then we pick the smallest node in its right subtree, which is 35, and 35 will replace the empty place. I mean, the 35 will replace 30. Okay, then the problem says, oh, now the problem is we want to delete 35. Okay, so 35 is a leaf node. It's a simple. That's the main idea. You see what I'm saying? Okay. So in the previous slide, I explained the algorithm to delete one node from a binary search tree, and if it was a little confusing, don't worry. We can explain that with this example. So I think it will be clear. Okay, so from this BST, and the problem is that we want to delete 60. Okay. In the previous slide, we said, okay, we can choose the largest node from the left subtree, or we can choose the smallest node from the right subtree. Okay, first, let's try to use the largest node from the left subtree. Okay, in this case, the largest one is 55. The 55 will replace 60. Okay, this is not yet done. From the first figure to the second figure, now in the second figure, the problem is a little simpler than the original one. So in the second figure, we want to delete 55 in the gray node. Okay. Then 55 is non-leaf node with a single child, so it's simple. 52 will be the right child of 50. Okay, that's it. This is how we delete. So delete one node and then choose the largest one, find the largest one from the left subtree, and then move that to the replaced node place. And then the problem is changed into a smaller problem. Okay, so basically we want to delete 55, and that's simple, so we are done. Or we can choose, from the first figure, instead of the largest one of the left subtree, we can choose the smallest one from the right subtree, which is 70, right? So 70 can replace the 60. Then that's simple, because 70 was a leaf node, so there is no further kind of consideration here. So just replacing the 60 with 70 is that's it. But when we implement an algorithm, we have to choose either of these two directions. Okay, then we don't know which one is. In this example, choosing the smallest one from the right subtree, it looks simpler than the upper directions. But actually, the upper one is better solutions. Basically, the upper one has well-balanced tree compared to the bottom one. The depth of the bottom one is 1, 2, 3, 4. But in the depth of the rightest one is 3, right? So actually the upper direction is better than the lower direction, but it depends on the original BST. Okay, depending on the original BST and the target node to delete, then we don't know which one is better. So in the algorithm, you have to choose one direction, the largest one from the left subtree or the smallest one from the right subtree. Or if you want, you can check the depth of the left subtree and depth of the right subtree, and then you can choose the longer subtree to have a more balanced BST after deletions. Okay. So when we work with the binary search tree, basically all the computation cost of the algorithms pretty much depends on the height of a binary tree. Okay. And the height of binary tree could be, with n nodes, could be n for the worst case, and it could be log n for average case. For example, when we have 5 nodes, and for the worst case, we can have this skewed tree, and in this case, the depth of this tree is 5, and that's the worst case. Okay, but for average, the depth of this tree is log n, because when we increase the depth, basically we can have twice as many nodes as before, right? So given the number of nodes, which is n, then on average height of the tree would be log n on average. Okay, then the computation cost depends on the log n, basically. Okay, think about the search operations. Okay, that's log n, right? So the balancing the binary search tree is quite important concept. So in this chapter, we didn't talk much about the balancing, but we will talk about it later, okay, in other chapter. Okay, this is it. So we just covered this chapter about trees. Okay, if you have any questions or comments, you know what to do.